Okay. My name is Peter Trapp. I'm Dean of the College of Science, and on behalf of the entire College of Science community, I'm very happy to welcome you to this installment of our Frontiers of Science lecture series. And this one's a special one because it's a joint lecture, the Friends in Chemistry and the Stang, Burroughs, Sessler lecture series. In a moment, I will turn the floor over to my friend and colleague, distinguished Professor Cindy Burroughs, who will do a proper introduction of today's very distinguished speaker. But I wanted to just lead off with a few comments about the lecture series itself. So the Frontiers of Science lecture series is the longest continually running lecture series at the University of Utah campus. It was started in 1968 by Pete Gibbs, who was chair of the physics department at that time. Pete Gibbs was a student of Henry Eyring, got his PhD with Henry Eyring, went off into the world with John Bardeen, and then came back as the chair of physics. And I think in those days, it's unusual for us to think in these terms, but in those days, the idea of bringing world-class scientists to interact with the general public was much less familiar than it is today. We didn't have TED Talks and things like that, I guess, back in those prehistoric days. But that was Pete Gibbs's vision, and there were a lot of frontiers being explored. Of course, you're all probably familiar with Vannevar Bush's famous The Endless Frontier report that went on to lead to the creation of the National Science Foundation. And so I don't know if that played into Pete Gibbs's thinking, but the very first Frontiers lecture was given by Gibbs himself, and it was called The Frontiers of Physics. And in the intervening 50 some odd years, we've seen a great number of distinguished lectures. And today we're going to have our 24th Nobelist in the series, so I'm very excited for that. So without further ado, let me turn things over to Cindy.
Okay, thanks very much. Thank you, Peter. It is really a great pleasure for me to be here to welcome Professor Ben Feringa from the University of Groningen. He's the Jacobus van Hoff Distinguished Professor of Molecular Sciences. That's maybe a fancy way of saying chemistry at the University of Groningen. And he's someone who is very well known on our campus and beyond, because he has a longstanding reputation in organic chemistry, and is especially well known, I think, on the American front. We often see him at American Chemical Society meetings, and so I've assumed that there was something special about Ben's relationship with the US. But then I looked at his list of awards. Okay. There are some American Chemical Society awards on here, like the James Flack Norris Award in Physical Organic Chemistry. Also, Peter Stang has had this award in the past. Dale Poulter, didn't you have this award a few years after? Oh yeah, I had it too. Okay, so we are a special campus of James Flack Norris awardees, and we'll have more in the future, I'm sure. At any rate, the Cope Scholar Award, there are many American Chemical Society honors to Ben's list, many lists of awards. But then I looked a little further and I realized it's not just ACS awards. He has the Marie Curie Medal from the Polish Chemical Society, the Nagoya Medal from Japan, there are so many, the Hoffman Medal from the German Chemical Society, the Raman Chair from the Indian Academy of Sciences, the Centenary Prize from the Royal Society of Chemistry. This is a long list, and I'm only giving you a few of those. But then, also impressively, he was appointed Knight and later Commander of the Order of the Netherlands Lion, first by Queen Beatrix of the Netherlands, and the later appointment was in 2016 by King Willem Alexander of the Netherlands. So he's actually very highly distinguished in many, many parts of the globe, and here I thought he was just ours. Anyway, Ben has such a world-class reputation because of his work in organic synthesis, especially with accomplishments in stereochemistry and chirality, in catalysis and photochemistry, chiroptical molecular switches, maybe we'll hear about that today, and putting all this to use to now try to build very small things at the molecular level. So Ben, we are so delighted to have you here today. Thank you for coming. So then, yes, we need to add this, and you don't need to use this microphone because you have two others.
All right. Okay, thank you, Professor Burrows. Cindy, I may say. We know each other for such a long time. It's absolutely is the micro on? You can hear me in the back? Okay. It's absolutely wonderful to be here, to meet you all again. We suffered for 2.5 years, not traveling, you know. I'm sure we have all shared the same experience. We can't send our students again to conferences, to ACS meetings around the world, which is an important part of their education. It's not only the professors, it's also the students. And it's a great honor. Thank you so much for being here, this lecture. And especially I have to thank, of course, Professor Steng, I know for so many years. Professor Sessler, Jonathan. Sorry, I don't wear a tie. I know they do that only in Austin, in Texas, you know, not in our country. And Cynthia, thank you so much for the hospitality. I had a great day here already today to talk with many of you, with the students and staff about the exciting chemistry going on. And I should not forget, when you look out of your office, you see mountains. In Holland, you don't see any mountain. Les Pays-Bas, it's flat, the Netherlands. So for me, this was already amazing thread yesterday when we went up, hiking there in the mountains, enjoying the beauty of Utah. But having said that, now hopefully we can enjoy a little bit of the beauty of chemistry, because I'm a synthetic chemist and I want to talk a little bit about the art of building small. So I often get the question, why do you need these molecular machines? Why do you build them? And probably the same question was asked, some type of question, to the Wright brothers many years ago, more than 100 years ago. Because when they were flying for the first time, people were asking, why do mankind need to fly? If God wanted us to fly, He would have given us wings. Of course, we get inspiration from the flying pigeon. We all admire the flying pigeon. But nobody would have realized that 100 years after the Wright brother, we built a Boeing 747, or forgive me for this is the European design, or the equivalent, the Airbus. But the fact that I could fly here to Salt Lake City, this machine, completely artificial, 3.5 million parts, built by chemists, material scientists, physics, engineers, computer science, all these different disciplines, made it possible that I could travel 10,000 miles, 1,000 kilometers an hour to come to your beautiful city. Try to do that with a pigeon. The flying principle of this Boeing or Airbus is a bit different, but it works perfectly. Try to get 400 people across the ocean with a pigeon. But we should also be very modest, because this is a triumph of science and engineering. But 100 years after the Wright brothers, we cannot build a pigeon. And when I talk with my biology friends, we cannot build a single cell of the pigeon. We cannot build one of the machineries of the cell, although progress is going quickly now. So we should be modest a little bit. So, why fundamental science? Because we often hear, what is the application? Why do you need this fundamental science? Which fundamental scientific questions and novel insights and discoveries were at the basis of your smartphone? And I suppose everybody has a smartphone. It was a long journey, a 50-year journey to change the world, because physics at the end of the 40s of the last century developed the transistor. The early 50s, the chemistry made the liquid crystal materials. Then the batteries came, and John Goodenow in the 80s, of course, he got a nice prize not so long ago. We would not have electric cars, we would not have power for smartphones if we would not have the batteries. The engineers made the device, the computer programs, etc., etc. My students cannot imagine that there was a world before the smartphone. And realize it's only 14 or 15 years at most that we have it, and it changed our world. Fundamental science and then innovation and technology. So the way to the future as we see it, the road to the future, is often one of the big question mark, because that is the most important in academia. What questions are we asking? And often we get lost in this beautiful garden, which is called the garden of knowledge and science. And then we hit upon questions that we have never thought about. And these are the most beautiful ones often. So, I'm a chemist, and I enjoy the beauty of the molecular world. The molecules we make, we design, etc. But we should not forget that chemistry is the creating science par excellence. So we ask fundamental questions, but we provide also challenges and perspectives for industry and society. And indeed, when we face our future, there are tremendous challenges. How to make sustainable processes and products, how to reinvent materials and energy carriers, changing the face of the chemical industry, go from trial and error to real molecular design of the drugs of the future. It's just a few of the challenges. And for those young people that think there are not enough challenges, look at this, there's a lot to be discovered. So, I'm a molecular scientist, I'm a chemist, and we build molecules and materials in the laboratory, and I'm glad that we have a universal language, because it doesn't matter if I'm in Utah, if I'm in Holland, if I'm in China, or in South America, or in South Africa. Everybody knows this is sugar, and this is the periodic table of the elements that we share. We have no borders, and I want to emphasize this, because nowadays, and we see this also in Europe, think about the war in the Ukraine, no borders. We go beyond frontiers, because we have our friends and colleagues all over the world. And this is also an important aspect of science: cooperation, international cooperation, and a passion for discovery. Go beyond frontiers to our future. So, in the art of building small, we are extremely good in making molecules. For instance, a very small molecule, 2 carbons and 4 hydrogens, ethylene, 160 million tons a year, the basic for a lot of our plastics. And we can discuss a little bit later about all the problems and the challenges we have with our plastics, But we have been tremendously successful. Or one of my hero molecules, it was called the Mount Everest of synthetic chemistry at the time that Woodward and Eskimos built it. Vitamin B12. This is a complex molecule: carbon, hydrogen, nitrogen, oxygen, phosphorus, cobalt, etc. But as far as I know, we produce only 35 tons a year all over the world, because you need only microgram quantities to stay healthy. But I would argue this is as essential as this molecule. Huge quantities, small molecules, big molecules, very complex molecule structures, tiny quantities. So, chemists are able to make the cables in the cars, the dyes, the drugs, the soaps, the materials for your clothes and your cars and the planes. Maybe we should be a bit proud to be a chemist. Despite all the comments we get, of course there are many challenges ahead, and I mentioned already plastics. Yes. But this is what we do and what we accomplished. This is what we are not very good at. This is what biology does in your body. All these dynamic functions, motion at the nanoscale. Look at this rotary motor, the bio-nanomotors that do the transport in the cells. Things moving from one part. The ribosome, the protein synthesis machinery, that's absolutely magnificent, this robot. The bacteria flagella motor. Can you imagine? This rotary motor that makes the bacteria swim in your guts, and they can go backward and forward. And then where we started, the optical switching, information processing in your eyes. And what I want to do is, this afternoon, take you on a small journey through our program, what we did over the years, and how we came, what we developed, including some very recent discoveries. So, we work on miniaturization of machinery, etc., motors, switches, dynamic functions. Try to bring dynamics, motion into molecular systems and materials. That's the main goal. And it was Richard Feynman already in 1959, you all know this, there's plenty of room at the bottom. What he meant is that people started with, for instance, chip technology and so on, smaller and smaller and smaller, and we are now down to the size of 10 nanometer or so, the latest chips. So top down. But of course what we do as synthetic chemists is bottom up. We build with atoms and molecules, small molecules, we build bigger molecules, etc. And it was took 50 years, you know, because before people could make the first small things that could move, etc. And I had the privilege to get a call from Stockholm together with my colleague Jean-Pierre Sauvage and Sir Fraser Stoddart. So, just one remark about nature versus synthetic. When you look in a car manufacturing plant, an artificial robot, these are really magnificent. I don't know if you all have been in a car manufacturing plant, but it's absolutely flabbergasting when you go there. These are these robots that build these cars. And these are hard materials, 2 meters in size. This is the robot in your body that makes a lot of the proteins in your body, of course, the ribosome. It's 24 nanometers. This is soft material. So realize this is a different world. And it's the effect of length scales and hard soft material. And we are not so much in getting motion, but about controlling motion. Because we are live in the world of low Reynolds numbers and Brownian motion rules. So, we started many years ago with this idea to build a molecular switch. So, I had the opportunity as a young professor to write a grant, and there was a project on materials, and I thought, oh, what should I do? And this is how I started. The idea, can I do information storage at the molecular level? And maybe even computing, using light, yeah, and using molecules, just like in your eye. And so the most beautiful switch, molecular switch, is of course the retinal in your eye. Hey, it goes from this band structure to a mollinear structure, light switch in the human eye. And you would say, okay, fine, why don't you take the retinal and build a device out of that? But that's not so easy. When you take it out of the protein environment, the opsin, you know, that it does not function very long because it bleaches, photo-oxidize, you get all kinds of things. But of course, this simple photoisomerization around a carbon-carbon double bond, a cis-trans isomerization, is the basis that I can see this lady and she can see me. Millions of these switches, yeah, trigger a change in the protein, a signal to the brain. But what is crucial, of course, is that it should be reversible. Because otherwise I would see you only once and then it would be over. So, we had to design switches and we built these overcrowded alkenes. You see here the stilbene molecule, the stilbene structure. And these are helical type structures. And we switch with 2 wavelengths of light between the 2 states. So this is robust molecules that we designed in the lab. You can tune the wavelengths and you can switch between these states. And indeed we could store information. You might wonder, why did we make them chiral? Left-handed helices and right-handed helices, M and P. Because one of the key problems with all these optical switching and materials was that once you switch with light and you want to retrieve the information, to read it, often you switch back because you interfere photochemically. But when you make them chiral, you switch between a left-handed and a right-handed form, you can go far out of the switching regime, detect O or D, and that's very powerful. So we took advantage of chirality to detect which state we had. So we make information storage systems. So this is what we recently did together with our physics colleagues in the clean room. So we make monolayers of switches, and these are gold islands, actually electrodes, and we can make optical data storage systems. So you might wonder about this. Together with the Philips company at that time, we make plastic where we wrote zeros and ones. And this is the potential of nanotechnology. So don't believe everything that is in the newspapers. That is the potential. Because the writing of zeros and ones at the molecular level, you need to address them. And you need the size, you know what the size of a molecule is, 1 nanometer or less, and you know the size of the wavelengths of your light. So easily we hit 10,000 molecules at the same time. So if we did single molecule switching, no problem. But then you have to isolate at the nanoscale, put here a molecule and put one outside on the campus somewhere so that they are sufficiently separated. But this is a principle if we could, so please, if there's some student who knows how to do this, help me, you know, because we are struggling here. But if we could address in a dense packing, in a monolayer, every molecule, we could write on one compact disk, compact disk is old-fashioned technology, I realize that. But we could write this megabytes, and that is to say, you could have one CD, and have music continuously for 240 years. So your grandparents and grandchildren could play the compact disc constantly for 240 years. This is the potential. This is not reality, because of the problem of the density. So, how do we make this overcrowded alkenes? Because these are very hindered systems, and we went back to a reaction that is very close to my heart, which was published in Perkin Transaction 1970 by Barton and Kellogg, good old Derek Barton and my colleagues Richard Kellogg, which is, because you cannot use a Wittig reaction or so, it doesn't work because the simplest system is, or a Peterson olefidation or so. So we make a hydrazone, we oxidize to the diazo compound, we take a thioketone, we do a 1,3 dipolar cycloaddition, you make an episulfide after exclusion of nitrogen, you get a double bond. So basically it turns out to you make two very reactive molecules, you make this heterocycle, you extrude nitrogen, you extrude sulfur, and then you have the double bond. And this works usually very well to couple two parts together with all kinds of functionalities, etc. So, now I will show you a few examples how we use these switches in a different context, and in particular to a more chemical biology approach. And we were very much interested in controlling a nanochannel. So this is the side view and this is the top view of the mechanosensitive channel from the coli bacteria in your body. Now why is it in there? Normally this is a pentamer, as you can see, this protein, and it's tightly closed, but it can open a 3 to 4 nanometer channel. And this is used as a kind of pressure valve for the cell. So if the osmotic pressure builds up, it opens a 3 to 4 nanometer channel, material can flow out. So we thought, can we use a switch to make a nano device that we can open and close on demand with a flash of light? And so this is what we did. We used here a spiropyran. This is another well-known class of molecular switches. You can switch with two wavelengths of light from the spiral form to the methionine form. And what you see here, you see a strong dipole, and you see that the molecule becomes suddenly quite hydrophilic. And so we thought, if we engineer the protein so that we can build in this switch, then maybe we are able to trigger to control. And that is what we did. So together with our friends in the biology department, we did modify the genome. We expressed cysteines. These blue dots are cysteines in the constriction zone of the protein. We hook it up with the spiropyran, and then we reconstituted it into the membrane of a giant vesicle, and we could open and close the pore at a single pore level, and we could demonstrate indeed that we could deliver a dye, a fluorescent dye for instance, or a drug out of this capsule. So this is our route towards making nanopores that we can control and open. And very recently, and this is very recent results, we went to a different system. This is the so-called FRAC protein complex. And FRAC proteins, they assemble into the membrane to form a pore, so a channel, by a helper molecule, and this is the sphingomyelin. And we thought, okay, if this sphingomyelin, this small molecule unit is crucial, why not replacing it by a molecular switch? And we used in this case an azobenzene, so from the trans you can go to cis. This is a well-known molecular switch. We engineered it to the protein, and you can switch it with light, and then suddenly it starts to assemble the proteins to form a pore in the membrane. And the beauty is, and I don't want to go through all the details, how we studied the pore formation, but believe me, we did extensive studies on the pore formation, etc. And we could establish that we have a single nanopore insertion. So we can control now with light the single nanopore insertion using this engineered molecular switch in this. And it was cytotoxic against cancer cells, so we are studying this now in a lot of detail. And maybe this is our lead towards molecular surgery in the future. And I team up now with people in the biomedical field to study this further. So I want to talk a little bit more on these switches, which came all the way from information to control protein function to control the function of drugs. Now when you go, this is called photopharmacology, the idea of making smart pharmaceuticals. And so when you go to visit a doctor, you want to have a drug that is active against whatever you have, an antibiotic that's active against an infection or so, or you want to have a painkiller. But what we want is actually a drug that is not active, a small molecule that we can activate on the spot. Because the whole idea is switching a medicine on with a light signal for high precision therapy. So imagine you have here an infection and you take an antibiotic. And we all know what happens then, you know, with your normal bacteria in your guts, etc. You don't want to affect it. But if you can activate it on the spot, that would be really good. And the same also, of course, for anti-tumor compounds, chemotherapy, where you have a lot of side effects often, nasty side effects. If you could have much higher precision therapy. So this is the goal of this research, high precision in therapeutic action by switching on and off the drugs. Does it work? So we focused on bacterial resistance because we are all facing in the past years the COVID crisis. But you know that the World Health Organization says one of humanity's ticking time bombs is antibiotic resistance. Don't forget, and I know there are people working on antibiotics here. I really appreciate our discussions today. And of course, cancer treatment for precision chemotherapy. So what we did is, for instance, we took Cipro, and I saw this molecule already a couple of times today, because in this department people work also on this. This is a broad spectrum antibiotic, and we thought, being a quite naive chemist, you know, we thought, oh, there are two nitrogens here, this is a heterocycle, let's replace it with an azobenzene. And it worked remarkably well. So you take the trans-azobenzene and the antibiotic is off, and you switch to the cis form and the antibiotic is on. And you can switch on and off, on and off. And so here is typically what you do when you grow cells of bacteria. And you see here we could grow a yin-yang pattern by using simply a photomask. And here is the activity. We can switch the activity. Because the cis form, as you all learn in your first year undergraduate, cis olefins and cis azobenzenes are less stable than trans, so thermally they go back. So we can precisely tune through the substituent effects, we can precisely tune the activity when they go back. So this one here with the para-methoxy goes back, you see, in 3 hours, and we have full activity again. Or it's completely off, of course, and then we can switch it on. So you can precisely tune how long it stays active. Because thermally it goes back. You can switch quickly back with light, but what is much nicer is you switch it on, and then it automatically is off after 3 hours, 24 hours, and whatever. When it leaves your body, no activity, no resistance build-up, etc. That's our dream. So we went also to some other problem, because when I talk with the medical people, they say, look, you have to help us with this bacterial biofilms, because with hip implants and all these things, this is a serious issue. How are these films formed? Because bacteria talk with each other, not like we do, but they talk via so-called quantum sensing molecules. And you see here a very small molecule. This is a typical molecule that bacteria uses to communicate each other to form biofilms. And so what we did is, we took such a quantum sensing molecule and modified it again with an azobenzene, and we had to do some modifications, you know, to make it biocompatible, etc. But the trans is off and the cis is on, and you see we have a 700 difference in activity. This was really huge, you know, and we can now control at the molecular level with light on-off bacterial communication to some extent. So we are really pleased with that. And the same holds for this anti-cancer compound. This is bortezomib, a proteasome inhibitor. We build in these azobenzenes, and also to some extent. This is not, let me make a warning, this is not ready for the clinic, but we work together with the medical people, the biochemical people, to develop this further and to see how we can avoid side effects. And my dream is a bit that we will, with the new imaging techniques, that you read where the tiny tumors are, you feed this information to your laser, and you write the activity of your chemotherapy. But there's one serious problem, and that is, of course, how to get light in your body. The medical people tell to me, oh, we can get light everywhere. Don't worry, Dr. Feringa, just develop your molecules, we will do the light. But we all know that there is this therapeutic window between 650 and 900 nanometers or so. And there is many groups around the world that work on making these switches, you know, going into the near-infrared regions that are high penetration depth, and I can use high penetration depth in tissue, and are useful for biomedical application. Because you don't want to use UV light, That's when we go to the mountains, you know, we have to take a sunscreen, you know. So red light, infrared light is what we have to do. And so we developed new ways to make azobenzenes with ortho substituents, And it's really nice. We took advantage of our lithium chemistry. Today I'm not talking about lithium cross-coupling or asymmetric catalysis. I'm sorry, that's another lecture. But we took advantage of our lithium chemistry, which is easy. Couple it with diazonium salts, and you can make all these highly hindered substituted azobenzenes, also with functionality for further hooking up to the drug. And these tetra ortho-substituted ones, they shift the wavelength all the way to the red. We can tune it. And so we can make antibiotics now, like for instance trimethoprim, with this red shifted antibiotics. And this is the first time now that we can go to do really in vivo and cell studies, etc., that we can use red light, and we can do that in tissues. So this is what we do, and there is a whole program on designing these molecular switches, which I will not discuss in detail today. But this was an important step, you know, to go all the way to red light, because that makes it possible that you do also animal studies, etc. Now, this is also a very small funny story I want to share with you, because due to the fact that we were able to make these red switchable compounds, we could incorporate them into these molecules. You see here a molecule long daisy, and I don't know if you have seen this in the literature. Yeah? This molecule is a small molecule effectuator of the circadian clock. And I came here by plane, and we all of us probably suffered to some extent, yeah, because our circadian rhythm has to adapt, you know, when you go from one continent to other. But much more important, we learned now that the efficacy of drugs depends a lot on when you take a drug, in the morning or whatever, and how it affects your circadian rhythm, how it affects the drug uptake and efficacy. And the circadian rhythm is there in every cell in the body. It's a very complex mechanism, but together with our Japanese colleagues, my PhD student Dusan Kolaski was able to make a light switchable circadian clock modulator, and we could change the phase and the period by 4 hours. So we can modulate, yeah, and this is in a cell study, it's not in your body, it's a cell study. We could modulate the circadian clock by 4 hours, by light, by an external signal, non-invasively. So you can imagine that we are very excited about this, because this opens up a lot of new opportunities to regulate cellular function. So, this to finish this part, the bio-nano future, you know, crossing borders between chemistry, biology, and medicine. I must admit, I learn a lot every day. I'm studying like a first-year student often, because I have to learn how to talk with the medical people, you know, to learn the talk language of cell biology. But it's fascinating when you come from a chemical background, because you think much more in terms of chemistry and molecular processes. But you know, the DNA and genome technology, we all know it will change our world. The network complexity, look at this. This is not the metro of Paris or New York or so, the underground of London. This is just a tiny fraction of your biological pathways. Actually, this is responsible for the blood clotting when you cut your finger, that you don't blood to death. This is 80 different chemical reactions integrated in a network situation. I don't know about you guys, but I'm already happy when I do one chemical reaction at a time and I get high selectivity. This is a network of 80 different chemical reactions responsible. Okay, rewiring the brain, optogenetics, this is a hot field these days. And of course, smart medicine, photopharmacology, I showed you some examples. This all has to do with how we can control in a dynamic way functions, yeah, building in these smart functions into. But I want to move on quickly to molecular motors, because this is switches and it's not a motor. So what about a motor? We all know that your body is full of motors and machines, and these motors push systems out of equilibrium. And I hear on television sometimes, and also in magazines I read, please be in equilibrium. If you read that, don't do. Because if you are in equilibrium, you are dead, biologically. Be in harmony, yeah, or in balance, that's all fine, but not in equilibrium. So, we all know what the things that move due to these motors. So, this is the most beautiful motor, yeah, that I know. This is the ATPase rotary motor. It's in your cell membrane. It generates the fuel in your body, and it spins, as you can see, yeah. Things go in and go out. You might think of these Formula 1 cars, you know, that have fantastic motors. These are way better, you know. This is my favorite. There are billions of these motors in your body, and they produce the fuel in your body. And my biology friends told me that they produce half your body weight every 24 hours. Now, I enjoy the food here, and I'm sure you do, but you don't eat half your body weight every day, eh? So this is all recycled. Can you imagine? So we talk a lot about recycling plastics and recycling our precious metals and all these things. We are simply not smart enough. We have to learn it as chemists, you know, because your body recycles half your body weight every day. Can you imagine? Biology has solutions for it. Anyway, this is what we face, the challenge. Molecular motors, how to control rotary motion in the nano world, not switching back and forth, but rotation, and how to control left and right. Because realize, if you are in your car and you equal probability going backward and forward, you don't get anywhere. Eh? So you either go left or go right. So how did we solve that problem? We took advantage of chirality, and it was mentioned already by Cynthia that I have a love with chirality. So this is the most beautiful example. It was called the Mona Lisa of modern science. I think we all can agree, the right-handed helix of DNA. But of course also the structures of the molecules, the left-handed protein, amino acids, etc. So we took advantage of that. We built these tiny motors, rotary motors, and you see here they are overcrowded alkenes. I told you how we make them. You have the central carbon-carbon double bond, you have a stator and a rotor, and they spin. And you see it spinning in a unidirectional sense. This is because we make it chiral, one form. You can spin it clockwise or counterclockwise. And it's a power stroke motor because the energy comes from the light. Now you might ask, how is it possible that you rotate around a carbon-carbon double bond as an axle? It's exactly the same as in your eye. Yeah, you excite in a matter of femtoseconds or picoseconds. You excite, you break the double bond, it twists. It's a cis-trans isomerization, nothing else. Why do we call it motor? Because we have controlled motion, we consume energy, we have a directional movement, and it's a repetitive process. Otherwise, it would be a switch. So this is how it operates. You have a stable molecule. We have two chiral elements, that is to see a helical structure and a metal stereocenters. And you see these metal substituents are in pseudo-axial orientation. And now we do the photochemical isomerization, and it goes from this helix state to this helix state. You see the metal gets in a pseudo-equatorial orientation. This molecule is higher in energy, and we figured out that it does a helix inversion spontaneously to position the metal substituent again in a pseudo-axial orientation, but if we have a different helix. And now we move again with a photochemical isomerization and a helix inversion. So in fact, a 360-degree cycle is two very fast photochemical double bond isomerizations, cis-trans, and two slower thermal helix inversions. And the slow step in this whole overall process that dictates the rotary speed is this helix inversion. You see 4 steps, 4 stages, yeah, that it rotates. So how do we know? I get this question often, you know. How do you guys know that it goes in a unidirectional sense through 4 steps? And I think when we discovered this first motor, we were lucky because it was slow. And we could see each step. So you can see you start here, you have a positive helicity, P, you have a positive CD. They have very strong CDs because they are helical structures. Positive, negative, negative, and you go through this cycle. You can nicely follow it with CD, you can follow it with NMR, etc. And we can do all the kinetics, the barriers, etc. And they are very robust. So the first motors that we made had a rotary speed of 1 rotation per hour. That's not much. You cannot build a car with it or do something special. You cannot really use it. But we were lucky because it was slow and we could see every step. Now we have made, I think, 80 different types of motors and so on. The fastest ones are well over 10 million rotations per second. I think we have faster ones, but we have difficulties to probe it, yeah, to measure, to determine that they are unidirectional. We team up with several people in the physics community to do look at the photoisomerization, the excited state properties, etc. The photoisomerization is in the picosecond regime. When you do the femtosecond laser spectroscopy, you can actually determine that very nicely. Now you can do all kinds of tricks to speed up, for instance, or change the wavelength. For instance, we build in this bipyridine type ligand in the lower part, in the stator part. Then you can complex to ruthenium. And now we can take advantage of the metal to ligand charge transfer band. We can tune the wavelengths. but also the speed through the metal, yeah, the angle, how wide we can make this gap here, you know, the helix inversion. And it gives us a whole new opportunities to make metal take advantage of this rich coordination chemistries. We also, what we do is we build antennas. So here, and I don't want to go into the details, but you can make here this kind of antenna that is very sensitive to photon excitation. And so what we do is we take this sensitizer, we use now near infrared light, then we do energy transfer, and we get the unidirectional rotation operating. So yes, you can tune the excited state profile using these tricks by sensitizing, and especially when you connect it to the motor, you get very nice. Now we have the whole wavelength regimes into the near infrared that we can use. You can also do other tricks. You might, like your car, you want to stop it maybe and then start again. So we put a crown heater here with an ammonium group, and we trigger with pH. You know, when it's bound here, it stopped. When it's deprotonated, you know, it rotates freely. When you can do it also with light. So we put a so-called Erie switch. Professor Erie has developed these diarylatines. So when this is in the open state, yeah, the motor functions properly. And when you irradiate then, and you close it to the closed state, you get a extended conjugation, and the photochemical rotation is off. So here with pH and here with light, we have an on-off switch for the rotary function. Now, we build these motors on surfaces in liquid crystal materials, polymers, and single molecules. And I will show you a few examples now about how we tackle some of these key aspects of these motor functions. I will not talk too much about polymers, but what we did is we used these motors as initiators for polymers, where you can change the helicity of the polymer or the organization. And it turns out that with one motor, you can control the helicity of a polymer, lengthy polymer, like a polyaxial isocyanate, for instance. But I want to focus a little bit on transmission and amplification. And so what we did recently also is to build this rotor here connected to the upper part of this motor. So this is a double bond and this is a single bond. So this is photochemically driven. So it goes like the motor that I showed you before. But now look carefully to this part, and you realize that this part always has the same phase to the stutter part. So here we have an example of synchronized motion. And so what we did is we looked at the moon. Because you know, soon your country will send a rocket to the moon. Hopefully next time there's no leakage of hydrogen and it will work. But you know, when you look at the moon, you always see the same phase of the moon. Eh? This is so-called synchronized motion. And when we ever want to make more complicated molecular machineries, we have to see how we can couple motions together, linear and rotary motions. So this is what my students did. It was a lengthy synthesis. It was complex, you know, to get all the barriers right. But ultimately we made it working. Now, where we are done a lot of work, and where we are several people in my group work on that now, is on liquid crystals. Because you all know what a liquid crystal is. You use it every day. Liquid crystals are these rod-like molecules. They are organized like beams in a river. And these are typical liquid crystal molecules that are in this place. And when you put in a chiral dopant, a tiny amount, you get this helical organization. And this helical organization determines the Bragg reflection of the light and makes it possible that you get the right color or a blue color, that you get the pixels in your smartphone or your display. Yeah? But we thought, what about a molecular motor? So we designed these special molecular motors. We put in 1 weight%, and then you generate this helical organization, and then you can contract and expand the helical supramolecular organization. It is mesoscopic materials. And you see, in about a minute, we can make every pixel, every color pixel, because it contracts and expands. It adapts to the chirality of this motor. And so, when you look at this surface, when you make a soft surface, look at your smartphone, you know. You know, when you push the glass of your smartphone, there's soft material behind it. Don't push too hard, because it destroys your smartphone. This is the surface. So this is a corrugated surface, you see that, the structure. And then what we did is we put a glass rod on top of it. And now with the motor in there, you don't see the motor because it's less than 1 nanometer in size. But let me see if I get this started. Okay, so what happens is when you swim, this is like swimming like a boat on the surface of this soft material. And you see this structure, the waves, you see the color change, yeah? This is real time, in the lab. And you see it spinning here, yeah, in a clockwise manner. I must admit, this was on a Tuesday afternoon at 5:15 in my lab. And this was one of these few eureka moments during my whole career. My students came to me and said, Ben, you have to come to the lab. And then they showed me where they did the experiment, and they switched on the lamp, and I saw this with my naked eye, without touching it. You're switching on the light, you saw it spinning clockwise, and we could spin it clockwise, counterclockwise, etc. Autonomous motion. Yeah? So, this is how it works. The helical organization, it winds and unwinds, you know, and that moves the object, it changes the color, it changes the surface. So we have these soft responsive surfaces, and we are exploring that now for all kinds of applications. One of the things we are doing now is to build in these motors into liquid crystal polymers. So you can make a polymer network, yeah, by cross-linking and using these motors. And now look, you can make these polymers, and depending on how we design it, we can bend, twist, yeah, here you see the twist, and we can move on the surface. So we have a piece of liquid crystal polymer now that walks over the table. You see? Now normally polymers don't walk, but when we irradiate with light, they walk over the table. They twist, they bend like an arm, like a muscle. And so this is what we do with our Chirality. Look, you can control now patches of these liquid crystal materials, and you can control the orientation with the liquid crystal, and then the way you assemble them, you can see you can make very complex motions just with light. And here you see an example where we have an R and an S, or an S and an R. And you get an outward or an inward motion of these materials, simply dictated by the organization in the liquid crystals, the control by this 1% of motor that is acting as a crosslinker in the material, and the chirality of the system that dictates if we go this way or this way. So, what about rotation and translational motion? And for that purpose, this was a nice challenge for us, because I had to write, I got a grant from the government, and the Minister of Science and Education was there. Peter knows this story. The Minister of Science and Education was there, and we had to tell in The Hague what we are going to do with this money. So I had to discuss with my student, and I said, I have to come with a good story, otherwise they will take away the money. So they said, look, these students from the engineering schools, they go to Australia for this car race, you know, this is the solar powered car. They have a great fun, you know, it's every year in September, I think, or so, this time of the year. But we are not engineers, we are molecular engineers. So we thought, okay, let's build a molecular car. So you see here the 4 wheels, yeah? This is the frame, this is 2 meters, this is 2 nanometers in size. This is not for fun, this was serious. It was because we wanted to show that you can go from rotational to translational motion. But realize there is a trick here. Because, I don't know if you realize, when you see a car moving on the street, look from this side, you see the 2 wheels going, the front wheels going clockwise, both wheels. But when you are behind the steering wheel, one goes clockwise and the other goes counterclockwise. So this is a mesostructure, and we had to design, because first we built the wrong motor, the wrong car. And it went like this, you know, and it didn't went straight. But then ultimately we could make it, and it moved over the surface. So this is the molecular car, this is the stereochemical design with the frame, etc. And then there is another aspect. When you lift your arm, and you move these motors, they move here, millions of these motors, and they move on the filaments to make it possible that you can lift your arm. This is the nano world. It's a bit different from the cars here on the highway, because this is how they move. So it's a stepping movement, you know. It steps over the surface, yeah. And you can imagine what we are currently doing. We're making highways, yeah, and to see if we can get them in a certain direction to one point or so. And that's tough, because this is supramolecular chemistry. Nature has figured out how these things walk without flying away. But now we have to get them on the surface. They should stick there, but they should also be mobile and moving and so. So this is a challenge that my students work on. But This is a normal modern electric car. I'm not sure if everybody has electric cars here already, but this is a modern electric car. This is our car manufacturing plant. You see, this is 1 billion times 1 billion identical nano cars. Our car manufacturing plant is not so bad after all. This is synthetic chemistry. So 2D confinement, I'm from the Netherlands, and so we like windmills a lot. So we thought it's really nice that you do this in solution, but what about attaching covalently to surfaces? Because when you talk with your people from device physics and so, they always say, okay, we want to have it solid on the surface, then we can do something. So we had to build rotors, axles, stators, and legs and put them on all kinds of surfaces, like for instance gold nanoparticles. And so this is what we did. Initially we put tile groups here. We all know they connect very nicely on gold, thanks to people like George Whitesides, and so we know all these tricks. We put all kinds of groups. We could put them on glass and other metals, etc. And it took us 8 to 10 years, to figure out that we had mono layers, that they indeed were spinning, all in the same direction, etc. This was not easy, but this worked out at the end. And so we built this nano windmill park. This is what our ancestors in Holland did 500 years ago. These are a bit smaller, 20 meters. These are 2 nanometers. But we have these mono layers, and they spin all in the same direction. And so we built these systems, for instance, to make responsive surfaces for wettability. And so look, here is a tripod where you have, for instance, a different orientation of your rotor. You have this piece of Teflon there. We can change the hydrophobicity, etc. We can change interactions with surfaces. We have a whole range of these molecules now that we make responsive surfaces for all kinds of properties. And you might ask again, what is the use of this in the future? I don't know. But the fact that you can make responsive surfaces, you can make things that move, you can think seriously, and this is under investigation now in quite a few labs, that you have self-cleaning windows and glass, that you have solar panels that clean themselves. It's not a problem in Holland because it rains all the time, but here in Utah with the dust in the desert it might be a problem. And of course that you don't have to clean your cars anymore in the future, but also self-repair, and because if you have dynamic surfaces under the influence of light, for instance, and you have a scratch, it might repair itself because you make this motile, and you can recruit monomers and it repairs. This will come. Maybe not with our motors, because they might be too expensive, but once you know the basic principles, how to make things dynamic. And in China, for instance, they work on self-cleaning windows. I've seen them actually. It's absolutely amazing. But what we do is we also use them to, here's a different way. We have 4 of these legs. We put them on glass, and then we grow stem cells on top of it. So we make these mono layers on surfaces, and we grow stem cells, and in this case we see dramatic changes, in the stem cell outgrowth, the shape, at the level of the protein and the DNA expression we can measure, and they are all consistent, and we are not trying to figure out how to use that, because stem cells are very sensitive to mechanical effects, and you can differentiate stem cells, and we try to use them now on these responsive surfaces. We do this together with people in the medical school. Now, 3D confinement, and I'm here in front of a hero of 3D confinement, making all these beautiful cage structures, etc. But we also thought about 3D confinement, and that is using muffs and cuffs, and many people in the world use these materials now. So we thought, can we take these metal organic frameworks, and in yellow you see here the pillars, and you see here the layers, and can we build these motors as pillars, in these 3D robust materials? And indeed, using these liquid exchange methods and using a motor with 2 pyridines and these zinc tetracarboxylates, we could indeed make this metal organic framework. You have to be careful, of course, that you have sufficient space that they can still rotate under the influence of light. But here we have this solid with crystalline materials, and then you might ask the question, how do these guys know that they still do the proper isomerization and rotate? Now we do solid state NMR a lot, and my hero Raman, and we take a lot of advantage of Raman spectroscopy, and that works really beautiful, and it's very, very good and very sensitive for this kind of material. So we indeed have now these solid materials where all the pillars are motors, sufficient space, and the layers are connecting them, and they are very robust materials. And now we went a step further because we took these porphyrins Yeah? Jonathan, you like porphyrins, I know, and extended porphyrins. So we take palladium porphyrins because they are sensitizers for our motor function. And so the layers now are palladium porphyrins, so they act as photosensitized, they pick up the light. The pillars are the motors, so we transfer now the energy. So we have now a double function system where we have the layers and the pillars, and they have, ultimately we get this responsive and dynamic materials. And finally, we make this covalent aromatic frameworks, and this is where we put most of our effort now. They are really robust materials, they are porous, and the motors operate. Yeah, we can operate, rotate them, and so now we make these materials that are like porous membrane type materials or sponges. They can, you can use them for gas storage or for separation technology, but due to the fact that they are responsive, we can trigger the events, the binding, etc. And so we use them now as smart membranes, responsive catalysts, but also as release systems, and ultimately, maybe that's a bit of a dream, as molecular factories. So we team here up with groups in Italy and so that have the proper techniques to do the solid state NMR measurements and the porosity measurements, because that's also very important. So finally, if I'm allowed, the last few minutes, I would talk a little bit about water and cooperativity and actuation, because it's all nice that we work with these motors and machines on surfaces and so make these materials and make a piece of plastic that works. But we were still triggered by the idea, and as we also work in the biological context now, can we do things in water? Because that is ultimately what you want if you interfere with biological systems. And so the idea was to make a kind of muscle. And we all know what a muscle is, and I mentioned before, you have these filaments and these motors, and they, like in your arm, and these motors make it possible that we can lift our arm. Not one motor, but remind you, millions of motors. And maybe some of these Olympic athletes might have a few motors than I have, but at least it works beautiful. Jean-Pierre Sauvage made a kind of an artificial muscle, yeah, from this molecular design many, many years ago. It was a famous example. But can we amplify collective motion from the nanoscale to macroscopic dimensions? Yes, it can be done. You can take responsive crystals like people did in Japan. You can make polymer materials. Guy Sapone took our second generation motor and make this polymer gels that can contract and expand. It works really beautiful. Nathalie Katsonis, she made these helical polymers. But the question is, can cooperative non-covalent interactions support an amplification, not polymers? And that's a different piece of cake. Because now we have to make small molecules that assemble in a kind of artificial muscle. So what we did is we took this motor, you see here a long hydrophobic tail, and we take these carboxylic acid groups here to make it an amplifier. And yes, indeed, they form nice fibers, supramolecular aggregates in water. So these are 5 to 6 nanometer dimension. Long fiber, but this is not a muscle. But then nature has all these tricks to assemble and to align, and I think Sam Stoop in Northwestern also used this trick a lot in his work. Take calcium ions, and calcium 2+ binds nicely to the carboxylates, and we thought, okay, maybe it starts to organize the whole thing. And yes, it works really beautiful. You see here the fibers align, we get really beautiful aligned fibers, and now we can simply draw a muscle from water. And I will show you, you see here in this cuvette, a freestanding muscle, or a free-hanging muscle. And if this movie, it works, you see we irradiate and it starts bending. Yeah? It will start bending towards the light. We can bend it away from the light depending on the system. So we have a small molecule that's an amplifier. It forms a supramolecular aggregate. Then we simply take this calcium trick to organize it, and we can take a muscle and we can lift a piece of paper with this. Of course, it's not very strong. And realize what you see moving here, ladies and gentlemen, is 95% water. Only 5% of the motor amplifier. So we have this molecule, we assemble by self-assembly, then we organize, we have an artificial muscle, and we can control with light. So small molecule, only 5-8% needed, actuation in water and air, lots of amplitude margin. This is not a polymer, it's just small molecules. And we do some mechanical work. It's not very strong, of course, and it's quite a weak system. But then what my students did is, they put in an amino acid here, histidine, you see? And this has the advantage that we can bind it now to iron oxide nanoparticles. And you see here the black dots, yeah? This is all the nanoparticles. So we have now again, a dual function system. That is a muscle that is responsive to light, but also the nanoparticles that are magnetic. And so with a magnetic field, we can, similar with a magnet, we can move them, we irradiate it with light, we grab a piece of paper, we move them with a magnet, we irradiate from the opposite side, and we release the piece of paper. And it works. And finally, this is what my student Xiaoyu did, and that is to modify the polar groups a little bit, yeah. So to get a slightly different muscle, and now we grow cells again in these muscles. And this was tricky, you know. Would that be compatible? But it works. And you can see here, this is these artificial muscles, yeah. And by using the common fluorescent techniques, and so you can see that these cells grow not only on the surface, but there is a lot of water, they grow inside, and we have now a kind of artificial muscle with these cells. And what we try to do now, and this is again stem cells, we try now to move, yeah, we do it also in muscle cells, to use the actuation of these artificial muscles and see how it affects. So this is a hybrid system where we have a biocompatible, and we can use it now together with real cells. And we're looking forward to see what will happen in the future. So today I shared with you how we start with molecules and go to dynamic molecular systems. We start from Mother Nature, yeah? The cells, the functions in your body. But of course, I'm a simple chemist, you know, I'm a synthetic chemist. We build molecules and materials. But when you think about trigger, response, and motion, you can maybe make smart drugs, and I showed you some examples. How to synchronize motion to go to real machine functions. How to make responsive materials. These are extremely robust. We make these materials, we heat them up to 300 degrees, they still function. It's amazing, I was surprised. Or to make artificial muscles, as I showed you in the last part of my talk. Do we make things moving? Yes. You see here, we can do translational movement. This is a nanocar. We have particles that move. This is rotation of the microrod. These are nano droplets, or micro droplets, sorry. This is a nano fiber that moves autonomously. And this is also a nanotube, translational movement. But this is chemical movement. I had no time to discuss this. What you see here moving is nanoparticles, or micro, yeah, this is a nanotube. This is an aggregate of these nanotubes. And you see, they move because they expel oxygen. And you know why? Because we put on these nanotubes glucose oxidase and catalase. So they confirm glucose. The fuel here is sugar water. Just sugar and water. That's it. And they move autonomously. It's not much of a control, eh? I feel sometimes like a kid playing, you know. But they move. Everything here moves in the laboratory without touching. So, this is the real most important slide. These are the people that made it possible, my team. These are my heroes, you know. They did all the hard work, because it's easy to talk about motors and machines and all these things, but you know, you have to make the molecules. You have to purify them. Then you have to do all the physical chemistry, to do the kinetics and everything. Then you have to get it on surface or into a biological environment to do the proper assays, etc. They did it. They are my heroes. The funding agencies, but above all, people that did the work. Now, I am really honored here to be here. You know, I had a splendid day discussing science and to meet friends again and colleagues. And it's a real threat, you know, I must say, after the COVID and this 2.5 years, to be able to meet people again, to discuss with students, you know, today, etc. It's wonderful. And then also to be honored with this lectureship here. Thank you so much. I got a different honor. You know, Holland is a very small country. And I gave a lecture for high school kids, you know, they came to the university. This was just before Corona, lockdown. And then they said, we want to give something to you, but he has already a gold medal, so what should we give to him? Yeah? And so then they looked at the States and said, what did his colleague, Fraser Stoddart, get at Northwestern, Chicago? Yeah? So there in front of the chemistry department, there is this big shield, 2 reserved parking spaces for Sir Fraser Stoddart, 2016 Nobel laureate in chemistry. Permit this. This is probably his limousine. This is how they do this in the United States. But I'm in the Netherlands and I bike to the lab every day. So in our biking shed, there is now this small plaque, yeah, that I can put my bike, and it says, bicycle parking space reserved for Nobel laureates. I'm really honored with that, and I park every morning my bike there, you know. So there is a distinct difference, you know, but that is, I'm still very much honored. And then I want to finish today with a message, yeah. This is my hero. In The Art of Building Small, Leonardo da Vinci said 500 years ago, when nature finishes producing its own species, man begins with the help of nature to create an infinity of species. And for all the young stars in the audience here, remember, imagine the unimaginable. The future is yours. Thank you so much.
Okay, Ben, I assume you will take questions.
Oh, sure. Please.
I just want to follow up with a couple of comments as people are formulating their questions. You know, I think it's just very interesting that many organic chemists think about synthesizing things in order to get to a structure. But in your world, it seems that you think about organic molecules in order to get to a motion.
Function, yeah, motion.
Accomplishments that I left off of your long list of awards is the fact that Professor Feringa actually completed in 1997 the 200-kilometer
Elfsteden tour, yeah. Yeah, don't worry.
In 12 hours. This is a 200-kilometer ice skate along
No, the lakes, the canals, the cities, everywhere there is water. They have a 200-kilometer trajectory, and this is indeed. I'm really happy that you mentioned. This was an event, you know, because this is 200 kilometers. It was minus 12 Celsius. There was snow. This is not in the ice hall, indoor skating, like the Olympics and so. This was outdoors. There were cracks, snow, and you have to complete in one day. It took me 12 hours exactly.
So,
but then I got this silver cross here. Yeah.
That's great. So when I was looking at the nanocars, it occurred to me that, you know, rather than thinking of this nanocar, it seemed to me it was more of a skating.
Probably yes. That's a good comparison, yeah, because it's not really comparable to a nano car or to a car, you know, in the street. You are absolutely right.
We're really pleased to have you here, and I want to also just point out that your being here is in part due to the fact that KLM flies a big plane over here nonstop.
Right.
But it's also due in large part to our friend Jonathan Sessler, who's in the second row here. Right? Jonathan is the Welsh professor of chemistry, Welsh chair, I guess, in organic chemistry at University of Texas Department of Chemistry. And he's been a good friend of Peter Stang and myself for many years, and then he decided, well, you know, this would be a fun place to visit and come see other friends, and so he established this lectureship a number of years ago. Thank you, John.
Thank you, John and Peter. Thank you so much for making this all possible. Please. Yes.
Yeah, I was interested in that last slide with the chemically powered motion.
Yes.
Could the next step be light-based control of chemically powered motion?
Yeah, that is interesting because we work also, I had no time to discuss this, to switch on and off catalytic function. We even made a system where we could have a chiral catalyst. We published this a couple of years ago, where we had a chiral catalyst that we could make a racemic compound, the R enantiomer or the S enantiomer of a product, because we can change the acidity. And we are now all looking indeed at switching on and off catalyst. And with this, not with this system, but this is a catalase reaction that I showed you here. But we have also the synthetic manganese catalyst that decompose hydrogen peroxide. So it's a kind of synthetic catalase, and they work marvelous. And indeed, we have not done it, but it's a great idea. If you can stop it and then switch it on again, then you can control the motion. Yes, absolutely. But there are quite a few people now working on this synthetic catalytic propulsion system, like Sen, yeah, and how is it, the person, I forgot, is it Chen in California, you know. There are several people working on this catalytic propulsion system. But indeed, to control it, because usually it's random motion. So we have to get an idea how to control it. Nature figured it out. We are not good enough yet. Yes, please.
Do you guys have an understanding or an idea of what kind of, I guess, payload capacity could be possible?
Yeah.
Like the work factor increases going on?
Yeah, no, that is a very good question. We have not done the mechanics in that sense. I team up with a professor in mechanics that really knows how to do these things, micromechanics and so. And we did some experiments. Of course, when you have a single motor or when you have a few motors, it's little. But what we do is of course we make these polymer systems or we synchronize motion. And this is a really important aspect, how to synchronize the motion of several motors. We have published a paper we published a paper where we try to make a monolayer and synchronize the motion and to see if we could get a stronger force. With the muscles, yeah, it's a small piece of paper, but that's about it, you know, not a heavy load. But this is a really important aspect to get towards how to amplify, I showed you examples, and how to then see what kind of mechanical function can you really trigger. Because also in your body, you know, single motors is not much, you know, I tell you. But it's due to the fact that you have millions working together and synchronized, etc. Yeah. But that's an important challenge. But I'm sure it can be done, because we showed with liquid crystal where they are well organized that it works beautiful, you know. These are really muscle type structures. Yes, John.
Absolutely fabulous. I'm delighted and honored that I could be part of the catalyst that brought you here. But that brings up this idea of maybe on your nanocore, can you put some catalyst in the back and go through styrene and leave a trail of polystyrene? So I'm thinking about trying.
Right.
So
of course.
Getting back to nature.
Yeah.
I'm thinking of a little bug spinning out.
Right.
Out a little thread.
Yeah, like the silk, yeah.
And so the whole trick is
absolutely,
not just doing this as a blob.
No.
So if I have a catalyst
This is
as a blob, I get a blob.
Yeah.
But if I have a catalyst in motion,
right.
then I get a thread.
Yeah, this is a fabulous idea, you know, to use it to control, to move in a certain direction, and simultaneously to see polymerization would be a good reaction to try, yeah, and to use that kind of function. And this is indeed what we try to do now, to couple this motion to specific functions. Right. I mentioned catalysts before, and I think the combination of motion and catalysis is a very powerful one, you know. There's a lot of, and polymerization, you are absolutely right. So we work in that context on, for instance, making trajectory to move it, you know, in a certain direction. You can do that by, for instance, electrostatic interaction or by surface modification. And to couple it indeed to catalytic function and so. We have not done the polymerization, but yes, and in the context of polymers, my student, what is he doing? At the moment, what he does is this flagella. You see, you saw this polymer that can move helicity. And it's really important. Movement in biology is often due to a helical movement, yeah, at the low Reynolds numbers. So we take advantage of these polymers indeed to get directionality to a movement. So thanks for the questions. Yeah, this is all integrated aspect of this movement, to go to polymers, to go to function.
One more question in the back.
Yes. Sorry, I didn't got the first part. Oh, okay, thank you so much. I appreciate that. Yes?
The science is awesome and you can so prolific. Can you comment on your management
Oh yeah. How I run my group is the following. I have quite a big team, about 40 people or so. But I have a problem. I'm interested in too many topics. Because we also have we do catalysis, asymmetric catalysis, lithium cross couplings, etc. I had no time to discuss it. We have a group meeting. Yeah, so I have postdocs, I have PhD students, master students, and so from 13 different countries. Just before the summer we had 13 or 14 different countries. We have every Tuesday afternoon, we have a group meeting, at 5 p.m. where a couple of students present their literature, they present their research progress, etc. But I have divided my group in teams. So I have a motor team, I have a bio team, I have a catalysis team, I have a smart materials team, and they come together in my office. I have an office with a blackboard, and we discuss every 2 weeks or 3 weeks, we discuss in the team, so that our postdocs, PhD students and masters, we discuss about their projects. And so each has its own project, but they work as a team. And it's really important, I like that, to have this discussion, not only about that you come with, oh, I discovered something new. That's nice, of course, but what is the problems? What is the real challenges? Do we understand? To discuss with each other, and that the senior students, give input to the junior students. Because you have postdocs. I have a postdoc from the States who comes from Harvard. He is a bright guy, and he can give a lot of advice to the young students about physical measurements, and so he's more in the biophysical area. So this is how we operate, and to help each other a lot. And it gives me also the opportunity to have a lot of discussion with the students. But we try to operate as smaller teams. So the motor team, the motorists in my group, they all work on different aspects of this motor program, and they help each other. And this is, and then I have, of course, individual discussions with the students and so as well. We also have fun. I mean, sometimes it's frustrating because you learn a lot from negative results as well. I mean, there are no negative results. You learn a lot from experiments where it was not that way, but it was there. And this is also great. And then we also have every year, but it was not possible these 3 years, we go with the team to visit some companies and to other universities. So I'm looking forward, because in 4 weeks from now, we go to Leuven in Belgium. And Leuven, I mentioned already to some colleagues yesterday, Leuven is the classic university already from the 14th or 15th century in Belgium, and it's quite a famous university. And we have a cooperation with some groups there. And we go to Johnson & Johnson there, which developed the vaccine, so we have a day visit to the company. And then we go to have a symposium together with Leuven. And then in the evening we have a barbecue, and I think we have a lecture about the chemistry of beer. Because the most important country for beers is not the United States or Holland, it's Belgium. Because they have, I think, how many different beers? 500 or so? It's amazing, these monastery beers, these breweries that are in monasteries, and so, they are very famous. And we are going to visit one of the breweries, and we go have to some nice discussions about beers and the chemistry of beer and so. This is also very important, All right? And this is how we run the operation. Yes. Sorry?
I'm happy to collaborate.
Okay, me too. I cooperate with a lot of groups in the world, we do that because we don't have.
That there's no beer at the reception that's happening right now.
All right. Okay. All right.
That a little bit later.
Sure.
Before that, though, I think Sigmund, chiroptical.
Oh.
Small gift for
Oh,
you.
thank you so much. I really
It's a
appreciate
nice
it.
small gift for you. Thank you guys for-
Thank you so much. It was my pleasure.
Oh, it was great.
Thank you. Thank you so much.
Perfect.
Reception outside.